Good morning, everyone. This week we will try to continue with our discussion on linearization for nonlinear systems around chosen equilibrium points. Okay, so let me get started. If you remember, the last time we talked about deriving the equilibrium points for a dynamic system. And we have given both the pendulum example as well as another general state space nonlinear system example. Now today we will go back to our pendulum example, and quite informally we will derive a linear approximation around one of the equilibrium points. Okay, so let me start with my discussion. So this is our week 3, okay, linearization continued. Okay, oops, sorry about that. So let's consider our pendulum system again. So this is going to be quite ad hoc to start with, but later on we will formalize this. And in fact, we will also expand it to forced systems and how we deal with systems with an input as well. Okay, so remember our dynamic system, x1 dot equals x2 was one of the state equations. x2 dot was equal to minus mgl over j sine x1 minus b over j x2 was our nonlinear system, right? This is in the form x1 dot is equal to x1 of x1 x2 and x2 dot is equal to f2 of x1 x2. In general, right, what we have is basically x as a vector dot is equal to f as a vector, and again state as a vector. If it's an autonomous system, we don't have any input. If it's a non-autonomous or forced system, we will also have input terms in these equations, right? So here is our nonlinear system, the pendulum system. Remember, it is basically a rod with length L on which a mass is suspended. mg is acting on the system. There is a viscous friction on this junction. So we have viscous friction B. And we could have a torque input to this system, a torque input tau, but for the time being it's non-existent because we are considering an autonomous system. Okay, so how can we find a linear approximation? So we know that x is equal to 0, 0 is an equilibrium point. Okay, so we have already extracted. So at this equilibrium point, right, x1 is equal to 0 and x2 is equal to 0. So both the angle over here, theta, is equal to 0, as well as theta dot being equal to 0. Okay, both of them are equal to 0. Now, if you think about the sine function, remember the sine function is something like this, right? And if this is, for example, x1, you see that this is x1 is equal to 0, the origin. And at the origin, if this is basically f of x is equal to x line, we know that sine x1 is approximately equal to x1 for around x1 is equal to 0. So for very small angles, the sine function approaches simply the x function. So the angle over here is 45 degrees at the start of this function. Okay, so So for small x1, we can use this approximation. And since this is the only nonlinear function in our expression, this basically approximates this function with a linear approximation. So my linear approximation, so linear approximation around x1 is equal to 0, x2 is equal to 0 is simply x1 dot is equal to x2, which was already a linear function, and x2 dot is simply equal to minus mgl over j times x1 minus b over j times x2. Okay, so if I wanted to write this as x1 dot is equal to a times actually I'm writing this vector equation at this point, right? X and a being a matrix, which usually I don't use a bold notation, but if you're using a textbook, you will see that vectors and matrices will be denoted by bold letters. Okay, so if I write this equation in this form, so what I'm gonna get is x1 dot x2 dot is the derivative of my state vector, a matrix A times my states x1 and x2. Okay, and from this equation, I can see that the derivative of the first state is equal to the second state. So I will multiply the first state by 0, and I will multiply the second state by 1. And in the second equation, I have a factor of x1 is minus mgl over j times x1 minus b over j times x2, and that's going to be my linear approximation. Approximation of our nonlinear system around equilibrium point x bar is equal to 0, 0. Okay? So one thing which is important is that we used an ad hoc procedure to find a linear approximation. The second one is that there is no such thing as a general linear approximation to a nonlinear system. Such an approximation is always around a chosen point in the state space. Okay? So this is, at this point, kind of heuristically obtained. So I'm going to now move on to like the formal procedure to derive such a linear approximation. Okay, so linearization around, let's say, linearization of state space nonlinear systems around chosen equilibrium points. And this is the autonomous systems case. We will later on extend this to non-autonomous or forced systems as well. Now, the formal way to do this, and we kind of partially covered that in 407 as well, is to use the Taylor series expansion. Okay, Taylor series expansion is basically to write any nonlinear function as a series. In fact, as an infinite series, okay, a series with infinite number of terms. So if you have any arbitrary nonlinear function, let's say this is our f of x, at this point it's a scalar variable x that I'm considering, but as we will see, this generalizes nicely to any vector function or vector or a multiple variables. Okay, so if you choose any point x bar over here, and we claim that actually at this point, around this point, okay, the function can be expressed as an infinite series, and if we truncate this infinite series, we can actually find this line. Okay, so this is the approximation, but the infinite series actually expresses the function exactly around this point, the only problem being that you have infinite number of terms. So how that is expressed, so f of x, this is an equality at this point, so the value of the function at x bar plus the derivative of f with respect to the independent variable evaluated at the same point times how much you deviate from that point. So if you want to write down, let's say this is x minus x bar is this distance, and you want to evaluate this function over here. Okay, so if this is f at another x1, okay, you can actually write it as, or I actually have written this as f of x, so let me write it like this. So f of x can be expressed in this way, but this is an infinite series, right? You keep deriving the function, taking the derivatives, higher order derivatives, evaluate at the same point, and you keep finding the distance, and you basically keep adding these terms as long as you want this to be an equality. Now, if you want to approximate this function with a linear function, okay, if you wish to find a linear approximation, you basically make this an approximation, okay? So, and you keep some of the terms. In fact, only the first term, which is the linear term, okay? So you take the same term, okay? X minus x bar, plus we call this usually the higher order terms, and what we do is we assume them to be equal to 0, and we get therefore an approximation, an approximate equality here. Okay, so this is the linear part of the expansion. Okay, so now let's go back to our state space system. Go back to our state space system. Now we have two issues, right? We have multiple variables, and we have more than one function. Okay, for example, if we have n is equal to 2, so x, the state vector, is composed of two state variables. In this case, you have x1 dot is equal to f1 of x1, x2, and x2 dot is equal to f2 of x1, x2. So we have two issues to resolve here. The first one is that our functions are a function of multiple variables. So we don't have only x, but we have x1 to xn. And also we have more than one function. Okay? So for any f x1, x2, including f1, f2, f up to fn, the Taylor series expansion becomes like this. So x1, x2, okay, becomes f at x1 bar, x2 bar. So this is my, later on we will see that this is going to be our chosen point, and this is going to be an equilibrium point, okay, with an implication, plus df over dx1. Now I'm taking the derivative with respect to the first variable. And then I have x1 minus x1 bar. Now this derivative needs to be evaluated at both x1 equals x1 bar and x2 equals x2 bar. Okay, which is the chosen point. Plus, now I need to continue to take the derivatives because the function is a function of both variables. So it's like changing in both directions. So I need to first take the derivative with respect to the first direction and then multiply with the deviation from the chosen point, and then take the derivative with respect to the second direction or the second variable. Okay, and then still evaluate the function at both of these values, x2 dot. Now this derivative, as we will see, both of these derivatives, both with respect to x1 and both with respect to x2, can be a function of both x1 and x2. So you need to fix x1 and you need to fix x2 in order for this to become a scalar coefficient. Okay? And now we multiply with x2 minus x2 bar. And plus, this normally continues indefinitely. So we have higher order terms. But what we do is that we ignore those higher order terms and we make this an approximation. Okay? So this is valid for any f. So we basically we will do this for f1 x1 x2, which is going to be approximately equal to f1 x1 x2 bar plus df1 over dx1 evaluated at x1 equals x1 bar, x2 equals x2 bar. So it becomes somewhat repetitive. Okay, x1 minus x1 bar plus df1 still over dx2. So f1's derivative with respect to x1 and x2, okay, evaluated at, let me shortcut this, x1 bar, x2 bar, times x2 minus x2 bar. So this is an approximation. I don't care about the higher order terms anymore. We do this also for f2, x1 and x2. Again, an approximation. Now I am evaluating f2 at x1 bar, x2 bar plus df2 over dx1. Again, evaluate at x1 bar, x2 bar, x1 minus x1 bar plus df2 over dx2, x2 minus x2 bar, and also this is evaluated at x1 bar, x2 bar. Okay? So now we have expressed both of our functions as linear functions of the deviations from the chosen point. Okay? So if I want to put this in vector form, where you have basically f as a vector function of x is basically equal to f1 of x, f2 of x, x being a vector. Okay? And therefore this approximation becomes f of x, x as a vector, and f as a vector, is equal to f evaluated at x bar, which is the chosen point, plus, now from the above I can get a vector matrix expression where this matrix is evaluated at x1, or let me again express this as x equals x bar, the chosen point. Okay? Now I need to put here these coefficients over here, right? So df1 over dx1, df1 over dx2, df2 over dx1 and df2 over dx2 times x minus x bar. Okay, so that's our vector matrix notation. Okay. Now this matrix has a special name. It's called the this matrix over here is called the Jacobian of F. Okay, or it's called the Jacobian matrix. It's nothing but a derivative matrix, right? So you see that on this on the rows you have the parts of the vector function. So the first row is f1, the second row is f2 up to fn, and the columns are with respect to each one of the independent variables. So the first column is with respect to x1, the second column is with respect to x2 and up to xn. Okay, so for an nth order system where we have x is an element of Rn, right? So x is equal to our state variables up to xn. F of x is basically also an element of Rn, because essentially for an nth order system you have n state variables, therefore you need to take n different functions to n different independent variable derivatives. Okay, so we have f of x being simply a set of functions f1 of x up to fn of x, where each x again is a vector. Okay, so in this case we have f of x as above is equal to f at x bar plus f times, f being the Jacobian matrix, times x minus x bar. Okay, and f, the Jacobian matrix in this case, is simply equal to all the set of derivatives df1 over dx1 up to df1 over dxn, and over here dfn over dx1 up to dfn over dxn. So what is this? This is basically the linear approximation of any vector valued function of multiple variables around a specific vector point x bar. Okay, so this is not specific to state space systems yet, but it's general for any vector valued function of multiple variables. So if you want to find a linear approximation to any such function, you can actually use the Jacobian matrix representation. Let us go back to our dynamic system. Now there is a further interesting point with our dynamic system. is that the chosen point usually is not arbitrary. That chosen point in our dynamic system is usually the equilibrium point. Okay, so in our dynamic system we have x dot equals f of x autonomous, right? And x equals x bar is an equilibrium point. So usually is an equilibrium point. So usually for an autonomous system, we have to choose that point carefully. It has to be an equilibrium point. What is the advantage of that? By definition, at the equilibrium point, we have f of x bar is equal to 0. Okay? So that's a further property of being at the equilibrium point. So what we have with the above discussion is that x dot will be equal to f of x, right? And that's going to be f at x bar. In this case, because of being at the equilibrium point, this is going to go down to 0 plus f times x minus x bar. Okay? Still, x's are vectors and f is a matrix. Okay? So you see that because of also the constant disappears, this becomes essentially a fully linear function without any offset as well. Okay, so this becomes x minus x bar. We will do something further. We will shift our origin. So shift the origin of the state space coordinate system to the equilibrium point. And what does that mean? That means I define a new variable. I define it as that deviation from the equilibrium point. So what happens is that the derivative of z, because x bar is nothing but a constant, we basically have z dot is equal to x dot because the derivative of a constant is equal to 0. And that means this expression f x minus x bar, x bar, simply becomes f times z. Okay? So we have z dot is equal to f, a matrix, times z. And this is now what we have as our linear approximation as of a dynamic system rather than simply an arbitrary function. Okay, so this is called a linearization of x dot equals f of x nonlinear dynamic system around the chosen, remember there can be more than one, around the chosen equilibrium point x bar. All right. Let me also put down a note here because this is a problem that I see often. Okay, note. Do not try to express a nonlinear system as a vector matrix notation unless you specifically find a linear approximation. What do I mean by that is that I often see a mistake being made is that you try to find the model of a nonlinear system and while you are trying to do that, you extract the equations and you immediately try to write that down as a vector matrix equation. The only thing you can do is to write basically a set of nonlinear functions in terms of the state variables. You cannot go any further than that. You cannot organize it as x dot equals a times x plus something and so on. You can only do that if you try and find a linear approximation to the system, and then obviously by definition you will get a vector matrix notation. Okay. Now I will continue with an example. Okay. All right. So let's consider an example. Actually, this is the same example that we also considered when we were finding equilibrium points. Okay. So let's do that. Now our system, the nonlinear system, is given by x dot equals x2 and minus x1 plus x1 cube. Okay, you see, this is the only form you can put the nonlinear system in. You cannot make it kind of a matrix vector multiplication and stuff like that because it's a nonlinear function. It's not composed of simply coefficients of different states, but you see that there is a cube of a state here. Okay, and we have also found that x bar is equal to 1, 0 is an equilibrium point. So we will try to find the linear approximation of this system around the given equilibrium point. So linear approximation around x bar. Okay, question mark. So what do we do? We first define a new state as x minus x bar, okay, which is equal to x1 minus 1 and x2. Okay. So later on, this is important because you have to always remember that your approximation is valid in terms of this new state. That means in terms of deviations around the chosen equilibrium point. Okay. Any solution that you find, if you want to go back to the state x, you need to consider this equation in order to go from the solution for z into the solution for x. Okay. So let's try to do that. So in the end, we will get something like z is equal to f times z. Okay. And this can be solved because it's a linear system, but you will get the solution in terms of z. And if you want to find it in terms of x, you need to still go and derive what x1 is and what x2 is in terms of z1 and z2. Okay, so these are my z1 and z2, the translated states. Let's calculate the Jacobian matrix. So I take the derivative of f1 with respect to x1. So here is x1, f1, the first row. It is equal to x2. The derivative with respect to x1 is equal to 0. Similarly, let's take f1 function and take the derivative with respect to x2 because it's only x2. The derivative will be equal to 1. Okay. Consider the second equation, the second line. So we have df2 over dx1. take a look. There is x1 in both terms in this expression. So what I'm going to get is that I will get 3 times x1 squared minus 1. Okay, so this is going to be 3 times x1 squared minus 1. In general, any such expression here, the derivative expressions, can be a function of both x1 and x2. In this case, we have some constants. We have an expression in terms of x1. And finally, df2 over dx2, since there is no x2 term in the second expression, we will still get a 0 here. Okay? Now, so that is my Jacobian matrix. Okay, so that is my Jacobian matrix. But remember that the Jacobian matrix is actually is the set of derivatives, but the derivative needs to be evaluated at x is equal to x bar, the equilibrium point, which is 1, 0. So x1 needs to be equal to 1 and x2 needs to be equal to 0. Okay? So therefore, f is equal to things that are already constants, 0, 1, 0. But also I need to evaluate this at x1 equals to 1, x2 equals to 0. If we put x1 is equal to 1 here, it's going to be 3 minus 1. It's going to be equal to 2. Okay? So, finally, we basically get z dot is equal to simply 0, 1, 2, 0 times z. Okay, so you see that this is a typical state space system with no input, an autonomous system, in the sense that you can do whatever you want with it using all the tools that you learned in 302. So as long as we stay around the chosen equilibrium point. Okay, so note. Okay, let me change color here. Solution for z will only tell you the behavior around the equilibrium point x bar is equal to 1, 0. If you wanted to find what's the behavior of x around the equilibrium point, you also need to use this equation over here, right? This equation. So we have z1 is equal to x1 minus 1, right? Also, z1 is equal to x1 minus 1. Therefore, x1 is equal to z1 plus 1. So if you want to find out about x1, you need to do that. And you have z2 is equal to x2, right? Therefore, simply x2 is equal to z2. So you can also find this behavior in terms of x by, again, translating back in the state space. But also you have to remember that you need to stay close to the equilibrium point for this approximation to hold. Okay? Let me also go back to the pendulum system again. Consider also our pendulum system. Now let's apply this general method to our pendulum system as well. Remember, we had just used approximation to the sine function. Now what I'm going to do is apply the full procedure. So I have x1 dot is equal to x2 and x2 dot is equal to, as per our nonlinear set of equations, mgl over j sine x1 minus b over j x2. Okay, So remember that we had equilibrium points, two of them. So we had x bar, let me call this 1, is equal to 0, 0. And also x 2 bar was equal to pi and 0. Now obviously you take the derivatives with respect to x1 and x2, construct the Jacobian matrix, but the Jacobian matrix will be evaluated to different matrices for these two equilibrium points. For this equilibrium point, and please verify this, okay, again, is that f will be equal to 0, 1 minus mgl over j minus b over j, which is the matrix that we had obtained by our ad hoc procedure before. But you can also evaluate the same matrix at this new, the second equilibrium point, and this will give you another f, a different linear approximation. Let's call this f prime. And this will be, and please verify this yourself, is that you will have plus mgl over j minus b over j. Okay? And, you know, like this gives you z dot equals f of z, one linear system. Okay? In fact, verify that this is the stable, this is a stable system. Okay, you can give just numbers, some numbers, and see how do you determine whether this is a stable system or not. Well, this is a linear system now. Okay, and for a state space linear system, you basically construct the characteristic equation, right, which is the determinant of Si minus A, and you equate this 0, find the roots, and the roots will be the poles of the system, the linear system, and whether these poles are on the left hand side or right hand side determines the stability of the system, right? This second system with the f prime is a different linear system, and in fact verify that this is now an unstable system by the same argument. Okay? So that completes our example. Let's break the video at this point. And up next, we will start discussing equilibrium points and linearization for forced or non-autonomous systems, specifically systems with input, right? So that's going to be slightly different from the case of the autonomous systems. Remember, for autonomous systems, we can have one or more equilibrium points. We may not have any equilibrium points. And we will see that it's going to be slightly different with forced systems. Okay, so I'm going to break it here.